Hello my dears, how are you all? So what we studied in the last class, I think we discussed some problems regarding the starting torque, full load torque, etc., right? And we did some, yes, we did some problem also, and we did the starting method, right? Starting method of induction motor, right? Like what? Direct online starting, auto transformer starting, and what? Star delta starting, etc. Okay, you just need to know the equations of each starters. Okay, so in the examination, direct question may ask like this starter is used, then what will be the starting torque to full load torque equation, or what will be the current, like we did yesterday, like some problem now 60% of the voltage will be delivered. So that is related to the auto transformer starter. So we just need that equation ISC divided by IFL the whole square into SFL bus. Okay, so that is the ratio of T start to T full load, right? So today we are going to discuss about testing of induction machine. Testing of induction machine. First one is no load test. No load test in induction machine. So for no load test as well as the full load test, we need the same circuit diagram. I will draw that now. Okay, so this is the circuit diagram for both no load as well as the blocked rotor test. Okay, so why we are using this test? What is the importance of using this type of test is that in the transformer we did what? No load test, I mean open circuit test as well as the short circuit test. In similar, what was the purpose? In order to determine the parameters in the equivalent circuit, right? R omega, Xm, I0, I omega, Im, right? R1, X1, R2, X2, etc. So these are the parameters in the equivalent circuit. So by doing that test, open circuit test as well as the closed circuit test and short circuit test, we came to know what is the value of parameters. Okay, what are the values of parameter? Similar manner, in induction machine also, there are two important tests we are doing for finding the parameter of the equivalent circuit. I already told you that the induction motor is similar to the transformer. Induction motor, the other name of induction motor is nothing but the rotating transformer. Other name of the induction motor is that it is a rotating transformer. So the parameters or the equivalent circuit is very much similar to the transformer, but there is a small difference is that here is an inclusion of slip. Here is an inclusion of slip. That is the only difference we can feel while doing the test in the induction machine compared to the transformer. So in the similar test which is in the transformer, that is nothing but the open circuit test. The similar test here it is in the induction machine is that the no load test. How can we perform this test? Simply we just apply the rated supply by using rated voltage, and we slowly increasing the current by using a particular starter. Any starter you can use, auto transformer starter, DUL starter, or starter, depending upon the application we can use anyone, and we slowly increasing the current and we make a rated voltage. I mean we make a rated voltage slowly, that's all. We make a rated voltage slowly and make sure that the rotor is running near to the synchronous speed or its rated speed. No load is connected here. No load is connected here. That is the meaning. No load test means no load is connected. The rotor is what? Tend to move or tend to rotate freely without any blocking, without any load. That is the meaning of no load. And note down the values of wattmeter. The total wattmeter reading will be, I will write in here, total wattmeter reading will be total wattmeter reading equal to what is W1 plus W2. It is equivalent to what? 3-phase power measurement we already studied, right? So total wattmeter reading will be equal to W1 plus W2. Let it be W0. Let it be W0. And we have to note the no load current. This is nothing but I0. We have to note the no load current, which is nothing but the I0. And the no load value of the wattmeter, which is equal to W0 equal to W1 plus W2, and the no load power factor, we already know this equation for 3-phase power measurement. The phase angle will be equal to what, my dears? Tan inverse √3 into W1 minus W2 whole divided by W1 plus W2 bus. If you know the value of this is nothing but the phase angle in 3-phase power measurement. The same thing you can utilize here because it is 3-phase measurement. So the phi 0 will be tan inverse √3 into W1 minus W2 divided by W1 plus W2, and from this we can find the value of cos phi 0 and we can find the value of what? Sin phi 0. If you know the phi 0, you can find cos phi 0 and sin phi 0. Then what is the equivalent circuit? What is the equivalent circuit in the transformer in no load condition? I will draw that. Equivalent circuit in no load condition. In no load condition. This is nothing but IM. This is the equivalent circuit which is similar to the what? Transformer equivalent circuit. Which is similar to what? Transformer equivalent circuit. R1, JX1 and I omega, this I0, R omega and JX sum, etc. etc. Okay? Because this is nothing but stator. Rotor is not considered here, right? Rotor is not considered here. That is why what? The simple stator connection. Stator is symbol to or equivalent to what? The primary winding of the transformer. The stator is equivalent to the primary winding of the transformer. So this is just the primary winding. This is just the primary winding equivalent circuit. Okay. So what will be the value of IW now? What will be, if you know the value of cos phi 0 and sin phi 0, I can say that my dears, IW will be equal to, what is that? I0 cos phi 0. Am I correct? And IM will be equal to I0 sin phi 0. Am I correct? And you found out the value of IW and IM. If you add this, you will give the value of I0, or simply this will be give the value of I0. This test, if you open circuit the test and make the rotor to full load, full speed, not full load, full speed, there will be a small current which is flowing, that is equal to I0. So you know the value of I0 also. You know the value of I0 also from that. You know the value of I0 also. Am I correct? So you know the value of I0, you know the value of W0, which is W1 plus W2, and cos phi 0, from that phi 0 you can calculate cos phi 0 and sin phi 0. If you know that, you can find IW and IM. You can find IW and IM. So what is the remaining parameter here? RW. How can we find RW, my dears? RW will be equal to, I can light V1. Let be V1. Let be V1. So I can say like V1 minus I0 into R1 plus JX1 whole divided by R equal to V by I, right? So it will be I omega. And XM will be equal to V1 minus I0 into R1 plus JX1 whole divided by IM. See? The value of R omega is nothing but, my dears, the potential across this R omega divided by the current, correct? The current is given IW or I omega, the current is given RW or R omega, we have to find, which is nothing but R equal to V by I, my dears. V by I, correct? R equal to V by I. That V is nothing but the voltage available across here. The voltage available across here will be equal to the applied voltage minus this drop, correct? So the applied voltage is nothing but V1. The drop across this R1 plus Gx1 is nothing but I0 into R1 plus Gx1, correct? So the remaining voltage will be available across this one, this portion. That voltage divided by IW will give the value of RW. Similarly, you will have Xm equal to V1 minus I0 into R1 plus Xm. You will have the value of Xm also. So you found all the parameters, correct? You found all the parameters, correct? So no load current, I mean the main important function of not all the parameter R1 and Jx1 we can't find, right? R1 and Jx1 we can't find. We can find I0, we can find R omega, we can find Xm, we can find Im, we can find I omega, and we can find I0. These are the parameters that we found from the what? Equivalent, I mean no load test, Okay, so that's all about the no load test. Next we have to see another test which is similar to the transformer short circuit test. Here it is called the blocked rotor test. Here it is called the blocked rotor test. The circuit diagram is saying no change in that. The circuit diagram is saying no change in that. Blocked rotor test. Blocked rotor test. Blocked rotor test. The same circuit can be utilized for blocked rotor test also, and the parameter here we have to find is that blocked rotor or equivalent circuit in blocked rotor test. Draw the figure. Draw the figure. Okay. So now in blocked rotor test, what we are going to do is we have to apply the rated voltage. We have to apply the rated voltage, and there will be some current, of course, which is nothing but the no load current. And what we are going to do is the rotor side, the rotor is connected with a shaft, right? The rotor is nothing but the induction motor shaft which is connected is called the rotor. So what we are going to do is we have to block the rotor slowly. That means by using a pulley arrangement. I think you already did in the laboratory. So this is the pulley. So by using this pulley, what we have to do, we have to slowly what my dears, we have to slowly tighten this pulley. I mean pulley, not pulley, this belt. You have to adjust the tightness of the belt. That is, you have to increase the tightness of the belt. Slowly what happened, this motor rotor now, this induction motor rotor now, its speed will decreasing. Its speed will decreasing, and again slowly we have to make that speed to 0. That means rotor speed to 0 value. That means we applied a complete blocking. We applied a full load. In the rotor. That means it is completely blocked. That is called the blocked rotor condition, and we have to note the parameters here, W1 plus W2 etc. You have to note down, and we will have WB, which is again nothing but W1 plus W2, and you will have the value of IB, which is nothing but blocked rotor current, okay, and you have WB also. Then you can find the value of, my dear, ZB is equal to VB divided by Z is equal to V by I, no? So VB by IB, where VB is nothing but the blocked voltage, where VB is nothing but the blocked voltage, will be VB and then be IB. Okay, so now you find the value of ZB, and there is another parameter which is called the, let be RB, which is nothing but WB divided by IB square. WB divided by IB square will give the value of RB, and if you know the value of this ZB and IB, or we can find the value of XB, which is nothing but root of ZB square minus RB square. So from that you will find the value of ZB, XB also. So this is nothing but, my dears, this RB is nothing but the R2 equivalent. This XB is nothing but X2 equivalent. The X2 and R2 equivalent are nothing but equivalent resistance referred to the rotor side. Equivalent resistance referred to the rotor side. I mean equivalent reactant referred to the rotor side. That is the meaning of R2E and X2E. That means similar to the transformer, we can know in short circuit test what we done in this short circuit test, we short circuited the high voltage, I mean low voltage side, and you applied the what high voltage side, I mean you applied the voltage in the high voltage side, and make sure that you applied a rated current in the high voltage side. So here we can't interchange rotor and stator like in transformer. In transformer you can interchange what I mean primary and secondary, because both are electrical, but here it is one, it is electrical side and another is a mechanical side. So what we are going to do, the same circuit is used for the purpose of a blocked rotor test also, but the parameter which is referring to the rotor side, we are referring the parameter to the rotor side, and it will be the circuit diagram. R2E and J into X2E. That is the equivalent resistance referred to rotor and stator will be the value. Okay, so the function of that main you have to see here. Okay, the problems regarding this will be it is not asked. Okay, it will not be asked. The problem regarding this will not be asked. But in the case of transformer, it was very important, because no load and blocked resistance transformer is very important. But you have to just know what is the test and what are the parameters we are going to find. So if you know the value of ZB, RB and XB, and you can find the value of what R1, R2, X1, I mean R1 equivalent and X1 equivalent, or R2 equivalent and X2 equivalent, depending upon the turns ratio and all, you can find that. Okay, that's also a very big calculation, but that part is not needed for us. For exam point of view, this is enough, just enough. You just need an idea what is actually blocked rotor. Okay, that's all. No question regarding this will not be asked. Okay, so if I take this whole session, in 5 or 6 months we can't complete this session. We can't complete electrical engineer, because in 4 years in extra laboratory sessions and all, we learned all this, right? If you want to know all this means, you have to refer textbooks, then you will get the full idea about what we have done in BTech. But as far as the examination point of view, this is more than sufficient. Okay, so next we are going to deal, and one more thing, my dears. Okay, this is enough. Not actually, this is enough. Okay, next we have to see crawling in induction motor. Crawling in induction motor. Did you heard about the word? Did you heard that word, my dears? Crawling. Crawling is nothing but due to the due to the harmonics in the supply, the motor will not take to full speed, that is the synchronous speed, near to synchronous speed. The motor will not take, I mean, as soon as we switch on the supply, but it will crawl to the speed of 1/7. Crawling means what? In order to, but crawling, you know the crawling, right? So crawled at a speed of ns/7, and it's continuously operating that speed only for some time. It will continuously operating that speed ns/7. Crawling is the meaning of crawling is that the inductor motor runs 1/7 of the synchronous speed is called the crawling. The induction motor try to run 1/7 of the synchronous speed is called the crawling. The reason for crawling is that mainly the reason for crawling is 5th and 7th harmonics. 5th and 7th harmonics. 5th and 7th harmonics. But there are third harmonics also. But that third harmonics will be cancelled or will be absent in balanced 3-phase supply. If you apply a balanced 3-phase supply, there will not be third harmonics. Before that, what is harmonics? Harmonics are nothing but we have the equation of voltage V is equal to Vm sin omega t and I is equal to generally I is equal to Im sin omega t. Harmonics are nothing but due to many of the reason the fundamental frequency omega in this equation, voltage and current equation changes, and in some cases it may be 2 omega, in some case it may be 3 omega, in some case it may be 4 omega, and in some case it may be 5 omega. But the even part, it is have a waveform symmetry and it will automatically cancel. But the odd harmonics are very dangerous. These will exist. Third harmonics, 5th harmonics, 7th harmonics, all will exist there. So the harmonics are nothing but these are the waves having the frequency which is the integral multiple of fundamental frequency. That is called the harmonics waves. That is called the harmonic wave. So why this harmonics wave make what problem? Means this is one of the problem. The harmonics wave make the rotor to run it is normal speed. What happens means the 7th harmonics notes very dangerous. Among these 3, 5 and 7 are very dangerous. So 7th harmonics will try to crawl, make the rotor to run at a speed ns/7, and the 5th harmonics will make the rotor to crawl at a speed of ns/5. So these are the crawling effect due to 5th and due to 7th harmonics. Due to 5th and due to 7th harmonics. How can we eliminate this crawling? It's not actually, we have to apply a pure wave and we have to make sure that there is no harmonics. Then only this crawling can be eliminated. So literally crawling means it is the ability or it is the nature of the induction motor to run mainly at this ns/7 speed. Mainly at this ns/7 speed, which is called the crawling. And these harmonics have certain characteristics. My dears. So first of all, 7th harmonics frequency. Suppose 7th harmonics frequency, harmonics waves or 7th harmonics frequency, which is nothing but 7 into Fs, where Fs is the supply voltage, and 5th harmonics frequency, which is nothing but 5 into Fs. That means it makes the frequency, fundamental wave frequency to that multiples. Suppose the 7th harmonics means 7th multiple, 5th harmonics means 5th multiple, and phase angle of harmonics. Suppose say 5th harmonics or 7th harmonics, which is nothing but 7 into 120. Phase angle means is nothing but 7 into 120. And what is that? 840. Okay, so it is nothing but 840 degree. So this 840 can be write like 2 into 360 plus 120. Am I right? 720 plus 120 is 840. So this is the phase angle. This is the actual phase angle of the harmonics. No, these questions will not be asked, but anyway we have to take precaution. What is the phase angle? So someone ask you what is the phase angle of fifth harmonics, means you have to simply multiply 5 into 120, and this equation, no, this is actually again coming from a long derivation and all, but no, we don't want that. We just need this shortcut to find the 7th harmonics phase angle and 5th harmonic phase angle, and multiply and make it in as a multiple of 360, because 360 is the complete rotation, no? Complete rotation is 360, so make it as a multiple of 360 plus something. That something will be the actual phase angle or phase difference of the harmonic phase. That means these fifth harmonics will try to rotate in that phase angle. Okay, the 7th harmonics will try to move in this phase angle, 120 degree phase angle. That's all. So that's all about the crawling. Okay, you just need to know the term only, my dears. You just need to know the term only. Okay. The similar term in induction motor relating to the crawling is that cogging. Another important term is that cogging. So these are one word type question, no? One word type. Next term, cogging or magnetic locking. Cogging or magnetic locking. What is that? What is that? What is that? If stator number of slot equal to rotor number of slots. If stator number of slots equal to rotor number of slots, then what happens? Imagine, my dears, suppose this is my rotor. On the periphery of the rotor there are number of slots, right? There are number of slots. If the same manner, in same parallel, suppose this is the stator. Here also some slots are there, no? If it is exactly parallel, means while rotation there is a chance of magnetically locking, because both the slots are parallel to each other. So there is a chance of magnetic locking. It will never lock in mechanically, because there is an air gap between stator and rotor, of course. So it will not lock mechanically, but there is a chance of magnetic lock between stator and rotor slots if both are equal, or stator slots by rotor slots equal to an integer. If this happens, that means suppose 36 by 12, there is also chance of magnetic locking. Suppose 48 by 12, there is also magnetic locking. Suppose 50 by 25, there is also magnetic, because all will give the values of an integer. So these are the reason for magnetic locking. So magnetic locking or cogging is nothing but if stator number of slots equal to rotor number of slots in the rotor, then there is a chance of magnetic locking between stator and rotor. Or suppose stator slots by rotor slot is an integer number, then also there is a chance of magnetic locking between this stator and rotor. It is called the cogging or magnetic locking. And how can we avoid this? To avoid what are we are going to do for avoid this magnetic locking or cogging is that we have to make skewing. We have to make skewing. Skewing is nothing but not making the rotor slots as well as the stator slot in parallel, but it is slightly skewed. Skewed means not making exact parallel, but it is slightly inclined, that inclined to some angle. Inclined in the sense what? Not the rotor itself not inclining, but the slots which are cut on the surface of the rotor, no, that is slightly going to incline. That is slightly going to incline. So what happen means there is never a possibility of what? Locking, magnetic locking between what? Stator slot we can't do anything, my dears. So stator is stator, no, so we can simply do the skewing on the rotor surface because that is very easy. So we have to make the rotor slots slightly skewed or in parallel with the stator slot so that we can avoid this skewing. And to make advanced level of skewing, to improve again, to fine level, what we are going to do, make a small angle, let be R, of rotor conductor with respect to the axis of the rotor. That means after skewing the rotor slots, the conductor also slightly to be what? Make a small angle. Then there will be perfect skewing. And there will not be any cogging or what? Teeth locking. There is another name. It's called the teeth locking. Stator number of slots equal to rotor number of slots is the condition at which what happen? Cogging or magnetic locking happens. Is it clear, my dears? Is it clear? Okay. Did you get my point? These are small topics. First questions are normally asked from this session. This is important. Next you have to see deep bar rotor. Okay, draw this figure. So deep bar rotor is used to improve the starting torque as well as to decrease the starting current. To improve the starting torque and to decrease the starting current. So for these two reasons we are using this deep bar rotor, and let's see what is its working. This is nothing but, my dears, it is the slot or the surface of the rotor, or simply the slots of the rotor surface is make it like it is made up of 3 elements. Normally what we are going to in squirrel cage, this especially it is where actually the starting torque problem arises in slip rim or skin squirrel cage. So this is happens in what? Squirrel cage induction motor. So this is for what? Squirrel cage induction motor. For squirrel cage induction motor, because in squirrel cage induction motor there is no provision to add any external resistance to the rotor side because it's permanently short circuited, correct? So what happens means, this is the rotor, suppose this is the rotor surface, and there will be what? The slight what? Impressions, right? Slight impressions, or there will be slight what? A deep what? Slot in the rotor. So in that we are permanently placing the copper conductor or aluminum conductor, that is we are normally done. But in deep bar rotor, what we are going to do, we what? Imprint, or we what? Insert a conductor like this instead of single copper or aluminum. That means this conductor is made up of 3 elements, element A, element B, element C. And what happen if we are using this, I will explain. Suppose at the starting time, what happened, there is a flow of current in the rotor because the rotor is short circuited due to Faraday's laws of electromagnetic induction. There will be a flow of current in the rotor, and due to the rotor current, this is a conductor, no, this is conductor, this is insulator, again this is conductor, this is insulator, and this is conductor. So these are 3 are conductors. So there will be flow current in this conductor, this conductor, this conductor, because these all are short circuited. So there will be of course the eddy currents due to the Faraday's laws of electromagnetic induction. So what happened, due to this current there is a flux around this. Okay, so only this, due to this, this is the flux, this is the flux, and due to this is the flux. So it will link the bottom conductor also, and due to the element A, this is the flux, this is the flux, it will link the bottom conductor also and the middle conductor also. And at the starting, this bottom layer Nomadius, this bottom layer C will experience high magnetic flux around it, correct? See, 1, 2, 3. 1, 2, 3 fluxes are surrounded around the element C at starting. So what happened? If flux is increasing around a conductor, its inductance will be very high because L equal to what, my dears? N phi by I. If the flux is increasing, its inductance also what? Increasing. If F phi is increasing, its inductance also increasing. If inductance increasing means the inductive reactance increases. The inductive reactance increases means the Z will be increases. Z will be what? Increases. If Z is increasing at a starting, if Z is increasing at a starting, which element offer maximum Z, my dears? Which element offer maximum Z? This element C offer maximum Z. So the current will, and after that this is the maximum impedance, and after that this will be the impedance, and the least impedance will be offered by the top layer. So the current will be intended to flow or prefer to flow on this top layer because this having least resistance or least impedance at starting, correct? So the current will be flowing through this section. This cross section of this section is very low. The cross section of the section is very low. What happened? So the resistance offered by element A will be, instead of, suppose we are not doing anything, we simply insert a single copper, then there will be a large cross section, correct? But here the cross section is not, only this area. So what happened? This area will offer a very high resistance to the flow of current. So initial current of this element A will be very low because of large, small cross section. R will be very high. R will be very high in element A. So the current will intend to flow or try to flow in the what? Top layer compared to this layer, my dears. These are very high impedances, never flow into this, but here it is a chance of flowing, but it contains a resistance also, It contains a resistance because the starting torque equation is directly equal to some constant kT into E1 square into R2 divided by R2 square plus X2 the whole square, correct? R2 square plus X2 square. That means the starting torque is directly proportional to R2. The starting torque is directly proportional to R2. So there is a flow of current in the element A maximum. So the starting torque will be very high because R will be very high because area of cross section of the top layer will be very low. So R will be very high. So starting torque will be very high. Starting torque will be very high. Clear? And less current will be flowing, of course, because the resistance is very high now. So due to that high resistance, what the starting current also very less. So we improve the starting torque and we reduce the starting current bus. Those two functions can be done by using what? A deep bar rotor. A deep bar rotor. Is it clear? Is it clear? These all are theory session actually, but questions are normally asked from this area because it's that much important. Because it's that much important. Because it's that much important, my dears. Okay, is it clear? Is it clear? So that's all about deep bar rotor. Next, double cage lot. Next, double cage rotor. Double cage. Double cage rotor, induction motor. Double cage rotor, induction motor. Outer cage, inner cage, See, this also for what? Squirrel gauge induction motor. These also for what? Squirrel gauge induction motor. Because in squirrel gauge induction motor, the problem of starting torque as well as the what? High starting current problem here is. So we have to eliminate that. So this double cage rotor motor is actually the special type of what? Double bar rotor. So in the previous class we studied about the double bar rotor. So same principle is applied here also. We have to make a small inner region, inner bar. We have to make a bigger outer bar. So what happened? The flux around this outer big bar will be very high compared to the small first layer or top layer. Now this is the only conductor cross section, but this is the conductor cross section. So the flux around this bigger region will be very high compared to this region. And the area of cross section of this region is high and this is low. So what happened? Normally under starting condition, what happened? The flux here it is very high. Flux here it is very high because it's a high region, no? See, you imagine like in the previous deep bar rotor case, what we element A, element B, element C, no? So the bottom region always experience what, my dears? Higher flux linkage. So here also the bottom layer always feel a higher flux linkage. No, because in the top layer, no, there is some very leakage flux in the air also, so it will not be linked with the bottom layer because it's very small. This area of cross section of the conductor is very small, so that the flux covered by that also very small. So the bottom layer normally experience very high flux linkage, so that at starting the inductance offered by the bottom layer will be very high, or the impedance offered by the bottom layer will be very high. So the current will intend to flow. This impedance predominantly due to the reactance, that means the inductance, and the current will intend to flow to the top layer. But the top layer having a small cross section area conductor, so this small cross section area makes the resistance of the top layer will be very high, so that the current will be flowing now at starting to the what? Top layer, to the top layer. And after machine picks up to the normal speed or synchronous speed, the value of slip will be very high, value of slip will be very low, so that if S will be very low means the induced EMF current frequency also what? S into F, correct? That means it will be very low, so that the inductance offered by the bottom layer under running condition or near to full load condition will be what? Very low. That means the current at that time normally spread between these two according to their wish, but at starting only we have to take care. So at the running condition there will not be much impedances offered by both these conductors, because there will be what? S into F times will be the induced EMF frequency. So due to that small frequency, the impedance offered by it will be very low, so that at a normal running condition it will provide a reasonable torque, and also at the starting condition the current will be flowing through this top layer rather than this bottom layer. So in the examination a question will be asked like this: in what double cage induction motor, the higher resistance portion is top layer or bottom layer? It is the top layer. Inner layer will have highest impedance and top layer have the highest resistance. That term you have to note, and the principle is same as that of the what? Deep bar rotor structure. Okay, that means the inner layer is always high flux density and outer layer will be lowest flux density. So inner layer will always have the high inductance or impedance, outer layer will have the high resistance only, not the impedance. Okay, and next, speed control of induction motor. These are special topics, right? Not that much important, but you have to familiar with the concept. The induction motor speed equation is equal to S is equal to 1 minus S into Ns, correct? So how can we write this again? 1 minus S into Ns is nothing but, my dears, 120 Fs divided by P. So speed control methods are one, stator frequency control, two, pole changing, three, stator voltage control, four, rotor resistance control, five, slip power recovery scheme. Slip power recovery scheme. You just want to know these names only. You don't want to what is and all. We don't want that. We just want the names. Okay, so just read these are the speed control methods for what? Induction motor. Okay, these are the speed control method for induction motor. Next, you have to note some important points, my dear. First one, induction motor is in motoring mode when the value of slip will be 0 to 1. It will be in braking mode when the value of slip will be greater than 1, and it will be in generating mode when the value of slip will be greater than 0. These three things you have to know. Directly a question will be asked from this. Okay, I already explained the torque slip characteristics. If S greater than 1 means it will be in braking region. Generating mode means S less than 0. Okay, write a question, my dears. Write a question. Okay, write a question. A three-phase induction motor is running at 1425 rpm, which while supplying full load, while supplying full load, its slip will be normally this type of question may ask because there is only one data. A three-phase induction motor running at 1425 rpm. What is the formula for slip? Slip will be equal to, or percentage slip will be equal to what? Ns minus n divided by n into 100. Correct? There is no mention, not any mention for this Ns, because only we have this 1425. So at that case, what we are going, normally we have to take this Ns near to the speed. And near to speed means it is nothing but 1500 rpm minus 1025 divided by Ns, right? Divided by into 100. So it will be equal to 75 divided by 15, or simply equal to 5%. So this will be the answer. So if you don't have any values regarding or for finding synchronous speed, then you have to take a speed which is near to the synchronous speed. That means near to the rotor speed. That is assumed to be as the synchronous speed. Okay. Suppose you have 1460. Suppose in your hand 1460. Then you have to take Ns equal to 1 by 1500 also. Okay. Suppose you have 2920 rpm, then you have to take, this is for nr, then you have to take ns as 3000 rpm. Okay, like that you have to take. If the data is not given, you have to assume a suitable value. That's the importance of this question. Okay, did you get the answer? Did you get the answer? Next, you have to write another question. A three-phase induction, 400 volt, a three-phase 400 volt, 50 hertz, 4-pole induction motor runs at a slip of 5%. The relative speed between rotor and stator magnetic field. Rotor field, okay. Rotor field and stator magnetic field. What is the question is? A three-phase 400 volt 50 hertz some induction motor, okay, anyway, runs at a slip of 5%, okay, happy. The relative speed between rotor field and stator magnetic field. What is that? What is that? We have to find the relative speed between rotor field. So we have to find speed of rotor field. What is that? That means the speed at which the rotor conductor is cut by, that is called the rotor flux. The speed at which the rotor conductor cuts by, that is called the rotor field. So the speed of the rotor field is nothing but the synchronous speed, because the synchronous lines of force are cutting the rotor continuously. So the speed of the rotor field is nothing but, my dears, it is simply ns. And what is the stator magnetic field speed, or the speed of the stator magnetic field? Magnetic field, which is nothing but again ns. So the answer will be, so relative speed between these two equal to what, my dears? 0 rpm. So this is the answer. So that is the answer. 0 rpm is the answer. Did you get the idea? Did you get the idea, my dears? Okay, so that's all for today. So let's begin a new session, that is nothing but DC machines from tomorrow onwards. So that's all for induction machines. Okay, that's all for induction machines. There are some special cases and special problems are there that we will definitely do in the previous year question paper analysis session. Okay, just for syllabus completion, we just need this. Okay, you have to continuously revise all these, just it is enough for the examination point of view. But again, special questions are there, some special questions are there that we will cover the when we are taking previous year question paper analysis. Okay, after the completion of the syllabus, we will go for the previous year question paper analysis, where you can fully solve, the all previous year questions in AE and JE examination, in all the states of India, which is asked for all the states of India. Okay, so we will do that. Definitely we will get time, we hope for the best. So that's all for today, my dears. So have a nice day, we will meet again. Okay, bye.